Hi everyone and welcome to this new video. We start with a new subject, which is AC steady state power, and we have of course several examples for this subject to clarify the situation in more detail. So let's start with the first example. This is the series RL circuit, which is connected to the VS voltage source, and the values are given here, and we have several questions which are the following. Calculate apparent power S, calculate the real power or true power, calculate reactive power Q, and calculate the power factor. Now, if I look at these four questions, I can make a drawing which will show clearly what's actually the situation for this example. So let's make a drawing of the power diagram. So I will make a drawing of the power diagram, because it's all about powers in this circuit. So let's make this power diagram. So we have the real and the imaginary axis. So first the imaginary and then the real axis. So we have the situation as follows. The real power or true power will be on the positive real axis, that will be P, and the reactive power, so the power which is dissipated or which is stored in the reactive components, which will be placed in the imaginary axis, and in this time it is in the positive y-axis because it's an inductor. For the capacitor it will be in the negative side, so this will be JQ, and of course we have the total of that vectorial sum of the two vectors that will bring us to the value of S, and this phase between the blue line S and the P is theta, and this phase theta will allow us to calculate the power factor. That's also actually the situation for the question D. So S, P, Q and theta, which will resolve the PF, and all of them, so four questions actually, are pictorial given here. So we would like to move this diagram and calculate the required values for that. Now for calculation of the P, for the S and the Q, I really need two unknowns, which are the current, the voltages, or the current and the reactance, or the resistance, or the impedance. So I really need more information from the circuit using the values here. So let's start first with the impedance of a total circuit. So the impedance Z is equal to R plus JXL. What is XL? Now, XL is the reactance of the inductor, which is omega times L, and omega is shown here in the voltage source expression 100, and the value of the L is 0.04, 40 millihenry. So if I substitute those values, I will have 100 times 0.04, which will result in 4 ohms. So that will bring us to the following expression for Z. Z will be 6, which is already given for the resistor, plus J 4 ohms. And I will convert this to the polar notation, which will allow us to calculate the other parameters and unknowns. That will be 7.21 phase 34 degrees in ohms. Okay. As you know from the power calculations for a steady state power, we need to use the RMS values for the current and also for the voltage. So if I look at the expression for the voltage source Vs, this is actually given in amplitude, so the 8 volts times the cosine of 100t in volts. This is just a peak value. So I would like to convert this to the RMS value. For pure sinusoidal expressions for signals, I can divide that by square root of 2. That's actually a familiar formula, and if you can also go through the actual formula for that, so that's also possible. So let's write that down first. So the V as RMS, that will be the Vs amplitude, the peak value, divided by the square root of 2. So it will be 8 divided by square root of 2, and that will bring us to 5.66 volts. Now, if I write this down also in phasor notation, so that will be the following. Because the phase orientation is 0 degrees here, I can add that information also. It will be 5.66 phase 0 degrees in volts. So this is actually an important parameter. So this will be used for calculation of the other unknowns. Now, which are what are they? Now we can of course use this voltage value for the Vs, and also we can use the supply voltage, which is Is, and from that I can come up to the total power or the apparent power. So if I continue with the total current Is, of course in RMS, I will have the following, which is the supply voltage in RMS divided by Z, so which is 5.66 phase 0 degrees, and divided by, as you can see, which is better if I write it down in polar notation for Z, so it is 7.21 phase 34, and if you calculate this correctly you will get 785 phase minus 34 degrees amperes, or milliamperes, or you can also leave it as amperes. So you will have the following expression for the supply voltage. Now if I continue, for example, the current for the resistor and the inductor, it will be exactly the same. So we already know this, so we can already say this will be also, since there's a series connection, so I will make this clear here, the series connection, so that will be IR RMS, will be IL RMS, and as will be also IS RMS. All of them are equal to each other because there's a series connection. Now if I calculate the voltage across this resistor and I use the current through that resistor, I can come up to the value of the P. And the same way I can use the current through the inductor and also the reactance of the inductor, and I can calculate the Q. And from that I can determine the S. So let's do that. So there's also other ways, but I will follow that question, the following form. So I will have the VR RMS, which will be equal to IR RMS times R. And if I write it down in the phasor notations, all of them, I will have 0.785 phase minus 34 degrees, and R is 6, but the phase orientation is 0 degrees, so I will have the following expression for this: 4.71 phase minus 34 degrees in volts. And if I continue with the inductor voltage, VL is equal to the inductor current in RMS times the inductance reactance, so XL. Again, the same current expression using the phasors, but now the value of the XL was 4 and the phase orientation is 90 degrees, because it is always in the positive y direction in the complex plane for XL, for the reactance of the inductor. So if I calculate this also, I will get 3.14 phase is plus 56 degrees and in volts. And if you look carefully, the phase difference between the voltage source of the voltage across the resistor, so resistor voltage and the inductor voltage, is always 90 degrees. That's actually a check you can always use to verify your calculations. So next step is actually the P and the S and the Q. So let's start with the P. So what is P? P, the true power, is equal to, now we have to be careful, the VR RMS times IR RMS, but we use the complex conjugate of the current. So what we get is following: I will have 4.71 phase minus 34 degrees, and I will use the complex conjugate of the current. That will mean I will use the current expression and I will make the phase, I will multiply it by minus 1, only the phase. So if this is, for example, plus 10 degrees, that will be minus 10 degrees. So in this case it's minus 34, that will be plus 34. So I will get the following. So this will be 0.785. I will write it down again. And this will be an asterisk. And as asterisk, we will have only effect on the phase and not on the amplitude. So this will be bring us to the following expression. So I will do it step by step in this case. This is the first time. So this is the expression when we work out the asterisk for the current, and I will have here plus to make this clear. If you have calculated this, this will actually make the phase again 0, but the calculation for the amplitude will be 4.71 times 0.785, and that will bring us to 3.7, and phase is 0 degrees. Let's actually check such that you know, okay, this is a phase orientation of 0 degrees, which is true, which must be true, as you can see, and the value is 3.79. So I already know the value of this arrow, or the length of that red arrow P is 3.7 in watts. Okay, now I go to continue with the Q, and specifically this is QL, so it's exactly the same. Will be VL RMS times IL RMS, again in a complex conjugate value of that. So that will be again the value of the inductor, so that will be 3.14, phase 56 degrees, and I will substitute for the current here directly actually the plus 34. So I will have the following expression. So if you work this out again using the rules for the phasors, you will get 2.5 approximately phase 90 degrees, and it's in volt amperes reactive. So what you can see is we already have also the phase orientation correct here to the 90 degrees, which is pointing in the positive y direction. And now it's the following situation. S is actually a vector, so we have to actually place an arrow on top of it. So P plus JQ, so that will bring us to S is equal to 3.7 plus J 2.5. And that is actually in volt amperes. That has its own expression. If I now convert this to the polar notation, that will bring us to 4.4 phase 34 degrees, also volt amperes. And what you recognize here is the following. This phase was already calculated for the impedance. So it's actually the same phase. Okay, now we have now the S, so the value of S, or the amplitude of S, is 4.4 volt amperes. So that is actually also true. Let's draw the situation for this circuit. So what we have is the following. We have the imaginary and the real part. So this length is P, which is 3.4 watts, and I will have the green, which is J 2.5 var, and which is of course equal to JQ. And I have the vectorial sum of both of those two arrows will bring us to the value of S, and this is the theta, which is again 34 degrees. Now is the situation for what is actually the value of Q, what is the value of R, so I mean P. So P, the value of P, actually the amplitude, is now 3.4 watts, so that's actually what we already know. The Q is 2.5 var. The S is here 4.4 volt amperes. Now is the following question, what is now the power factor? The power factor, that's the last one, the power factor PF is equal to the cosine of the angle theta. So PF, that will be cosine of the angle, but I have to be very careful by placing here a leading or lagging. So what is the procedure for that? So how do you make this clear? Now, if this is a positive phase, you will place a lagging. If this is a negative phase, so if the theta is negative, you will place a leading here. So actually the leading or the lagging will be determined by the current phase. So if you look at the current for the supply voltage, which is actually already negative, so we actually mean that we have a lagging power factor. So this is actually the following. This will bring us to, so if I this will be lagging. I already know that because it's positive. And if I have 34 degrees, this will give us the lagging, and PF will be 0.82 lagging. What you want is, of course, make the power factor unity, such that the total power delivered by the supply voltage will be dissipated in your ohmic part of your system and not stored in the reactive components. That's actually for this example. As you can see by drawing the diagram, we'll clarify the situation in more detail, so I will advise you to do that before you dive into the calculations. So make a sketch such that you can see where you have to go and follow the steps, and you can find out the unknowns pretty straightforward following the steps. So I will see you the next time, and keep in touch, and good luck.